Right, so the intent of this is to skip over a lot of the motivation and background and say more about like where this comes from and all the great details and stuff. So, but just to remind you of the problem, suppose we have an algorithm A and it takes some t time. Usually t is a function of the input length. And we want to find an algorithm B that's equivalent to A. Usually A just outputs a bit, so we want B that outputs a bit that has minimal space usage. Okay, so it uses the minimal amount of memory. And we use this, I think this is some function of t itself. Okay, so just to get our bearings for all reasonable models of computation that we want to think about. So like we're asking whether time t is contained in space f of t, and we want to minimize f. We want f to grow slowly as possible. So something like this is obvious for most models. Like we could occupy at most constant number of bits in each new step. So we might, so anything running in time t, we will take order t space. There are other models where this might not happen, like in a so-called word RAM model where you allow constant time operations on log n bit words. If I'm measuring space by the bits, then that might make like a log factor. But if I'm measuring space by the registers, typically, like I'm processing at most one new register per step. So still, I mean, we would say that time t is in space order t. Okay, and so the first interesting thing about this problem is that this is not the best f you can possibly do. So prior work showed that for essentially all reasonable models, you account for space in sort of the way that I was describing, you can get t over log t. So that's starting with Hopcroft, Paul, and Valiant, and box 75, and Paul and Reichhoek in 81, and then it was Halpern, Louis, Meyer, and I think Weiss in 86. So and these papers were titled On Time versus Space, On Time versus Space 2, and On Time versus Space 3. But I refrained from calling mine On Time versus Space 4. Maybe you could, if you write a follow-up. That title is still up for grabs. Yeah. So 1 and 2 and 3, and I mean, effectively, what they showed was this one worked for multi-tape Turing machines, which I will recall for you later if you don't remember. This one worked for something called like a tree computer, which effectively means that it's a Turing machine, but instead of having a one-dimensional sequential tape, the bits or the cells are arranged in a binary tree, in which and in any step you can go left, right, parrot. Like that's the head movements. Okay. So and then in doing so, they also got some results for random access machines, and then this generalized all that to like other models, including pointer machines and all kinds of nice things like that.
How does this tree model compare with most RAM models?
So usually it's in most like a log-in factor overhead, which could be a problem if you're trying to save a log factor overhead. So usually when they talk about these simulations, they're saying, okay, if I'm in, tree model, how much space in terms of bits am I using in tree model? Or if I'm in like RAM with like log cost, where like, so log cost meaning like I measure like the number of bits that like an operation takes, then I better measure my space in terms of bits too. So like, as long as you're being fair about like which, like you're using the same model here as which are here, then you get the log t factor. Yeah. Yeah, but like, if you could improve like the result that I'm going to describe for like tree computers, this would be a big breakthrough, and it would basically show you would have it for all random access machines up to polylog overheads. So tree model is very good.
So is it fair to think of tree model as like, paying some logarithmic cost to access a typical cell?
Yeah, okay, it's like you can imagine an array,
Yeah.
which is implemented by just having a complete binary
Binary
tree
search.
of log the size of the array.
Okay.
And when I want to access it, I just like jump up to the root or jump up to the least common ancestor and go back down.
Okay, perfect.
Yeah, so that's why it's only a log extra factor called it. Yeah, so once you can implement an array, you can just do basically anything you want, right? Yeah. Right, so I will focus more on this simulation, even though it's sort of the weakest one, but it's the one that we can get a better result for right now. But we can talk more about like what is in the way of improving these, okay? So right, the model of computation, we'll say it's multi-tape Turing machines. Okay, now's the time to draw a picture, okay? We have a Turing machine M with some state, and it's got some number of tape pads accessing different tapes. One has the input, say X on it, the rest start with blanks. And a single step, I read and write to all K cells, whichever one, let's say this one is like looking over here. They can all be looking at sort of different places. They read and write, they change the state, and they move left to right on each one of these tapes independently. The transition will just tell me, tape bits telling me whether to go left, right, and so on. So the heads can be arbitrarily far apart, and this actually makes them surprisingly powerful. Already for two tapes, they're very powerful. It's a very robust model. So for example, like the circuit value problem, circuit evaluation can be done in nearly linear time in this model. So I give you an arbitrary logical circuit. I want to, and I give you an input. I want to know its output. This can be done for circuits of size n and in polylog n time on multi-tape machine. So this sort of result means that actually the only thing that could separate multi-tape Turing machines from grams is the possibility of not knowing what register you're going to look at, like at some point in time. If I give you a circuit, then you know exactly at every point in time which two registers am I going to read and where am I going to put it, right? So those things can be handled by multi-tape. So the only thing that could possibly be is if like you have some sort of control flow saying, oh, if it looks like this, then you read this, and if it looks like that, you read that. So circuit value problem is in polylog n. It's very easy on this thing. Related to that is sorting. You can do lots of different sorting algorithms.
Can you say, like, in a couple sentences, how the two tapes allow you to do this circuit value so quickly?
Yeah. There's a couple of ways to do this. Right, what is the easiest way to describe this? So, I mean, one way to say is that actually multi-tape Turing machines allow you to implement priority queues, like which sounds like priority. So where you get to store values, like you insert a value, extract them in. You extract the minimum. I mean, that sounds like it needs random access, but with amortized polylog time, you can do it with a multi-tape Turing machine by basically like storing like exponentially increasing lists, where you're like doing the inserts, and then you sort. Each of these are going to be maintained as sorted, but like when you push something into a list and it spills over, and it's so that was to the I, you go to the I plus one, then you like sort of resort it. Like, so there's a way to maintain a priority queue. So once you've got that, you can process the circuit in sort of topological order, where I push the values from like each gate, like sort of let's say I know in the future, like reading a certain gate, I know in the future when I'm going to need
Right.
those values. So I can push those values like on my priority queue. Then when I reach that gate, if I extract them in, right, if I've extracted all the previous numbered gates of 1 through I, then I extract min I plus 1, I'll get like all the inputs I needed.
Cool.
Yeah, so that is something I actually discovered this summer. Like there are more complicated ways to do it with recursion, but so I was trying to find some example like that would separate these two. I actually realized priority queues can be implemented.
Even in this.
Yeah, even in this sequential thing, yeah, but you need amortization though. It cannot be done. Like you cannot do it in worst case time, like because you've got like a tape, right? Like if the thing's in the wrong place, then but amortized over like many operations you can do. Yes.
So now, just a quick question about this. Does it matter how the input was stored in this context of circuit value? Like the order in which like the gate?
Yeah. So I'm assuming that it's stored in topological order.
Okay.
Okay, yeah, because, I mean, for the purposes of simulating a circuit, yes, but I think that topological order can also be done in your linear time, but it's unclear even the literature thinks about that. So I'm just gonna, let's just say that it's in topological order. That's, in other words, I already have the gates numbered 1 through n, and I have edges from I to j, only possible when I is less than j. Okay, so, yeah. So, yeah, circuit value, sorting, I think the standard merge sort, it's not too hard to see how you might do that with a multi-tape machine, like a merge of 2 lists, it's really moving pointers. But also things like fast Fourier transform, like integer multiplication of polynomials and stuff like that whole class of algorithms can be done in near linear time. Like your favorite matrix multi algorithms, which are recursive, let's say based on Strawson or something like that. Because of their recursive structure, they can be done with multi. So there's a wide variety of things that can be done. So getting good simulations for them makes a huge difference over, say, a single tape machine where we know you must have quadratic overhead. So like a big open problem actually is to find any problem pi, like a decision problem, which is in, say, time, let's say I want to put subscript RAM to say it's on some random access model in linear time, but is not in time. And if I don't put the subscript, I mean multi-tape Turing machine, like say n polylog n. So trying to find like any problem, decision problem, which can be done in linear time on RAMs, but not in n polylog time. RAMs is a major open problem.
So no conjecture even, like this?
Yeah, I mean, I have looked at various problems like, I mean, I think you can, if you work hard enough and you put enough bells and whistles, you can cook up some problems. I mean, you can cook up problems which are almost as hard, like basically reduced to the linear time, like simulating a RAM in linear time. Like I'll give you the code, but yeah.
Is there any like reasonable graph problem that you think captures that problem? Or?
That's a good question. I don't know, like the natural sort of pointer chasing types of problems, many of them can actually be handled by sorting, sorting the right things, like in the right way. So, no, like, yeah, there are. It's not like there's no candidates whatsoever. It's just that, it's not clear what to believe, I think.
Even if the problem isn't natural, it's just like, take a universal like RAM model. And
Oh, yeah. I mean, that is as hard as possible. I give you the code,
right.
a random access machine, I give you an X, I give you like T1s, does it hold in time T? That's as hard as any of them. Yeah, so that's like the best candidate you could think of, but at the same time, reasoning about that is as hard as this problem. Like, there's no real difference in that problem, thinking about that problem and thinking about this, right? That's just the notion of completeness. Yeah, so it would be nice to have something a little more structured,
So maybe I'm naive, but is it plausible that this could be false? As in there is no such problem?
It's plausible, yeah, it's plausible.
Okay, so you're saying that.
I thought for sure priority queues couldn't be implemented.
Okay.
Okay,
So
yeah.
even for this problem, we don't know if you can't do it in like in a multi-tape Turing machine in polylogan. Like,
Yeah, sorry, which thing do you,
like the universal.
yeah, that's as hard, that's equivalent to this problem.
Yeah. So I'm okay.
It's equivalent, like what you said, like showing that that thing is in time multi-tape Turing machine and polylogan is equivalent to finding any problems with. Yeah, it's complete. Okay. Yeah. Yeah, so, right, so a question that people asked was whether this f of t could be made smaller, like t to 1 minus epsilon for some epsilon. I guess for a long time it was conjecture. This is not the case. So, for example, like one of the first papers on theoremization, Sipser showed that sort of assuming no, okay, no plus some explicit expanders, these are explicit or mergers, whatever those things are, which were later, so these were later constructed by Sachs, Srinivasan, and Joe. So, but assuming both of these things could show that P equals RP. Luckily, we know now that you don't need to get a lower bound, like a space lower bound against time in order to get the randomization. We just need circuit lower bounds against time. So, right, so later work of Nissan Vigderson and Aljozo Vigderson and so on shows that just showing things like time to the n is not in size, the IO not even infinitely often in size to the epsilon, and will imply things like P. So, but the question of whether you could improve this was, or whether you, what can happen from assuming you cannot, this motivated early work on derandomization.
Does the model matter for this question? Like, is this a question in the context of the RAM machines or?
Oh, it does matter in the sense that for one tape machines, it's been known since the 60s, you can get square root of t.
Okay.
So for a one tape, single tape machine. On the other hand, we've known quadratic time lower bounds for single tape machines also since the 60s for, you know, very closely related reasons. But yeah, so, but I mean, that's just sort of an artifact of information.
Yeah.
Theoretic stuff.
Just
Reasons like,
palindromes requires quadratic, right?
yeah, like just by communication complexity of equality.
Oh.
Like from this you can derive like a quadratic type lower bound. But like getting a simulation is a different thing. I mean, I could sketch how that works later. It's not hard, but yeah, I mean, this was sort of like the first indication that at least in the single tape case, quadratic lower bounds are, it's not hard to come by if you can get a square root improvement here. Right. So, okay. So, right, so that so that's sort of all the motivation now for the main theorem. So in the multi-tape model, we have time t space square root of t log t. And this holds for essentially any time function. It doesn't have to be, turns out it doesn't have to be constructible. I mean, it needs to be, just to be fair, it needs to be at least linear. Mainly because we're doing a space-bounded simulation. We don't actually need it to have these usual properties of constructible. Like we could try the simulation I'm about to describe with t equals set to n, t set to n plus 1, t set to n plus 2. Or if you don't like that overhead, you could double it, you know, each time. And then until the simulation gives us an answer. Like the simulation will either, you know, give us an answer. It will basically say definitively yes, definitively no, or I don't know. So that's the way our simulation will work. So we can just keep increasing the space budget till it works. Okay. So as a corollary, we get that the circuit value problem can actually be solved in square root. of the circuit size space, which is, I don't know, I think that's maybe the most surprising consequence to me. Like it seems to me that if you think about evaluating an arbitrary circuit, like any way you might do it, like if it's arbitrary and it's, there's some parts of it are expanding, you feel like you need to store like a lot of wires, like you can easily have lots of cuts that take omega n to store the bits, but you can get square root here. Like another corollary from the non-uniform perspective is that like size S circuits have branching programs of size to the O tilde square root S. So this is interesting when S is subquadratic. A branching program is just a decision tree where you get to reuse nodes. So it's like a decision DAG. In every node, you query a variable. If it's 0, you take an edge label for 0. If it's 1, you take an edge label for that. There are two sinks, 0 and 1 with the answer. Right. So this is some very non-trivial branching program upper bound for linear size circuits, for example. So another important consequence, which we're stating, is that for all space functions, at least, as space of S is not contained in time S squared over log squared S. So for example, linear space cannot be in significantly subquadratic time. Now, this is something that people widely believe was true. In fact, because we believe P is different from P space, we believe that space S is not in time S to the K for every constant K. So we believe that's true. And this just happens to be one of the weirdest possible ways you could ever prove such a statement, by showing something that nobody really believed was true to show something that everyone believes is true. In fact, we believe that this is probably exponential in S. In fact, it should be, right? So I can show you the proof. It's a few lines, given what we have. So make sure I save the lines just right. So let's say this is not true. So space S is contained in time S squared. So suppose like space S is in time S squared over log squared S. By our simulation, right, we can take a square root of that. So we'll get square root of that quantity. And so now we'll have it in space little O of S.
But you need the square root
Extra
log.
log, yeah, but.
Yeah. Log. This. Yeah, that's a log squared, so it's the low of S, and we have a contradiction to the space hierarchy theorem. It says as you strictly increase space, there are strictly more problems you can solve. Space hierarchy. Right. Yeah, that's why I put log squared. Right, and one thing that is important to note is that so some of these results about multi-tape Turing machines are very, very sensitive to the multi-tape model. So for example, so we know by Paul, Kippinger, Simoretti, and Trotter, 83, that in the multi-tape model, deterministic linear time is different from deterministic linear time. Okay, but already, like if I want this to be, let's say it's a two-dimensional tape, okay, where I have a grid of cells, okay, I have like two different tapes with two-dimensional grids, say. already with this like small change in the storage structure, it becomes an open problem. And so if I put a two-dimensional here, we don't know, so. Okay. Whereas, for this simulation, at least we can, get results for larger dimensional tapes. So this gives some indication, to me that, the approach we're doing is not so sensitive to this like single tape model, and in fact is more robust than I think. So for example, we can show that time, so this is for D-dimensional tapes. It could be, think of grids or cubes or something like that. T, this is in space. So T log T to the appropriate exponent. The appropriate exponent should be 1 minus 1 over D plus 1. Okay, so that way we get square root for D equals 1, and it degrades a bit like 2/3, 3/4, and so on. Okay. And so we get lower bounds against space for those things as well. And I mean, one more thing. Yeah,
So space is also D-dimensional tape, or it's like single tape?
So for nice thing about space complexity is that those kind of things don't matter so much. As long as I'm fair about how I count the bits of storage, right? Like if I don't care about time anymore, I could just take my two-dimensional storage and just write it down cell by cell on my one tape machine and have like little markers to indicate,
Yeah, I see.
here and there where I am on my 2D tape. And then, if I don't care about time, like I could just sweep across the whole thing and.
But if you need to store like the I don't know, like the coordinates, then you need to pay extra like d log t space.
Yeah, so there's ways to sort of write down like the boundary and write down like the region in an efficient space. So like, because like if I don't care about time, like I could just store this in almost any efficient representation.
So that result even holds for like non-constant d.
But so this will hold even in the one tape case for space. So like,
Is there any condition on d, like any constraint like
this will hold for any constant d. What you mean, or does it hold for unbounded d?
Yeah.
We probably have to be a little careful about there's probably some dependence here, but it's easy to work out. We can work it out later. It's just like one equation we have to think about. It's an interesting question, like maybe because like in log dimensions, maybe you can embed a RAM a little bit better or something else. Like, yeah. I've thought about that sort of stuff. Yeah, there is some extra dependence on D. We have to be careful, like maybe some multiplicative or dependence on D. Yeah. Right. Okay. So I guess maybe that's all I want to say about overview, other than, if we could improve this to space, P to the epsilon for all epsilon, then we would separate P from P space. I don't know about whether we can do that or not, but it is already an interesting open question to, in the one tape case, get a better simulation, get something like, so this is for one tape. T, big question marks, whether we can get space. P to the half minus epsilon. So whether we can improve it even a little bit. If we could do that, then basically by the remarks I was just saying about how in the one, like if I have like space slightly less than square root, then if I got something like this, I could take my RAM model, I could simulate in quadratic time on this, and then I'd get a better than quadratic improvement here, and so I would actually have some nice space simulation for RAMs if I had something like this. So even improving this square root for the one tape case is a very interesting.
That's an impressive eraser.
I know, that's what I
Thank you,
was
thank you,
thinking.
thank you. I can send you a link, an Amazon link.
So effective.
I don't get any, kickback myself. Yeah, it's
Have you reached out? You could get a
Part of my Blackboard
sponsorship.
code. What's that?
You should reach out to get a sponsorship.
I should.
Mathematics departments all over the world.
Yeah, it took some trial and error. Actually, the ones at MIT, some of the erasers aren't so bad, but, yeah.
How long does it last?
I don't know. I've had this for over, I've had it for at least an academic year. And so it lasted through, what, 50 lectures so far, I guess? I don't know.
How often do you clean it?
Every time, basically. Like I run water on it and let it.
Oh.
Wait, well, okay.
Would you say it's worth the low price of $10.99?
I don't know. It could be a hand model. Yeah, it's good. It's good. Yeah, the low price. Right, so let me describe how Hopcroft, Paul, and Diane works. I mean, it's very important for what we do. But I'm gonna first describe it in a way that's actually more general than the multi-tape case, and it's sort of like captures the way that the on time versus space 2 and 3 also work. So we're starting with the multi-tape machine M and an input X. We want to simulate it. We're going to think of some graph-theoretic way to model the computation. So the first way we think about it is having some directed acyclic graph with nodes 0, 1 through t. So 0 representing like the initial configuration. And so we'll have like content for each of those nodes. So content 0, I'll just think of it now as being, the initial configuration. So it's going to be like start state, and so start state, and the input X, all that stuff. And then content of I, is this going to be, let's say it's the transition taken in step I. Okay, the transition in step I. Because that will tell us the state that we're in, what we're reading, what we're writing, what we're changing to in terms of state and where we're moving. Okay, so I have a little example to try to illustrate what I mean. Very little example. So let's say I'm reading 3 cells, and in step 1, I move here. Let's say I overwrite with 0. Step 2, I move here. Step 3, I move here. Step 4, I move here. Okay, so then this graph we can think of as like, okay, in step 0, right, like that's sort of like, when I have an arrow every time I'm reading something from the input, I'm always going to have like a chain. I always need the state from where I just was to compute the next. So I'll always have this sort of chain. But then, right, I'm going to need to read the input for step 2, and also going to step 3. Now for step 4, right, I need to read what I wrote in step 1, right? So, oh, sorry, what I wrote in step 2. So yeah, so in step 2, this was 1, 2, 3, 4. So in step 2, I wrote a 0, so I need to edge from there to there.
Why do you need the input in step 3?
Oh, actually, do I need it? Well, yeah, in step 3, I'm reading this, which is part of the input, and then I'm moving here. Right, so that's why.
How do I know if you're reading something or not? Do you need the input in every step, or you don't?
No, I don't. Like, so for example, in step 4, I'm reading what I wrote in step 2.
So you don't need the input because it's already.
Because it was written, yeah, so it's like, I basically had to keep track of where I last wrote and then put the edge there. So one of these is telling me like the state, like the sort of the spine is telling me the state, and this is sort of telling me what I need to read, like, which is where I last wrote.
Okay,
That's
so
why I
when you
put this extra
enter,
edge.
when you enter a location.
Yeah,
You need whoever wrote last, so if it's the input, you need the input.
yeah, exactly. So yeah. Exactly, yeah. Okay, yeah, so this thing is sort of modeling, you know, well, what information do I need at each step and when did I compute it last, that kind of thing. And, right, and the idea is that I'll have, right, these edges that ij just means that like I need content I to get content j. Right, so I need to know like what I was reading, I need to know the state. And then the goal of, you know, if I'm thinking about computation here, the goal is to get content t, the last node, because that will tell me, right, if I accept or reject. So that's what I want. And so to sort of get a space efficient simulation, thinking about these kinds of DAGs, we also note that even if I have multiple tapes here, right, I'm going to have, you know, a constant n degree for each of these things. Like there's only like a constant number of bits of things I need from the past to understand what I'm doing in the present. So to model this, we have some constant n degree graph. We're going to define a pebble game. Okay, that we play on this DAG. It's going to have 3 rules. So I can put a pebble on any source. This is like saying I can compute the initial configuration or bits of it anytime I want. Okay. Then 2, so I want to model computation, right? So I want to say like, okay, if I've pebbled all n neighbors of a node I, then I can pebble I. So in other words, if I have a pebble on 2 and 3, I can pebble 4, for example. That's exactly, you know, how computation should be modeled, right? Right? And I can remove a pebble at any time. And, you know, I really want to remove as many pebbles. You know, I want to aggressively remove a pebble anytime. So we can think of modeling space complexity as what's the minimum number of pebbles I need to pebble the last node in the stack.
I have a question. So why is one node has 2 inputs, like two incoming edges?
One? Why, which one?
Like in the DAG example you just showed.
Yeah, why does what have 2 income?
Why isn't like at any step you just read what you see right now and then make your move or like editing this cell? Then isn't this just depending on on just this bit at this cell itself? Why it has 2
So you
income?
probably also need the
You
state
need the state,
from the last.
you need the state from the previous too. You need, right, to know where you are in the program, you need to know the state. So this is tracking the state and these are tracking the reads and writes.
Oh, so that's like 2 different types of edges. Like there are flows of edges for the configuration and
Yeah.
those-
Yeah, see, it's like, in a program, this would be like the program counter, like the line number and like whatever, like the variables you're reading.
I see. And there are additional structures, is it? Like for example, I can view the 4th step because it reads the stuff that the 2nd step writes.
Yeah,
And I can think of it as I also make changes to this cell and then
Yes.
Like all future time steps won't be
yeah,
requiring.
they won't access 2, they'll access 4.
Yeah, I see.
Exactly. So this thing has lots of structure. In fact, that structure is exploited a lot in the thing that, like the thing I put up here about non-deterministic linear time different from deterministic linear time. That like, yeah, so if you, a modification of this DAG, which I will describe later, actually, yeah, means that this is a union of a constant number of planar graphs, for example. Like they're very, very structured.
Oh, wait, so you are not assuming the machine is oblivious?
No, not here, no, not at all. Yeah, I haven't said the word oblivious, so we can, yeah, there's no oblivious.
Which means like the DAG depends on the input.
The DAG absolutely depends on the
I
input.
see.
Yeah, so, yes. It will depend on the input. Right now, we're not worried about that, but we should be and we will be. Right.
The DAG is fixed by the input and the Turing machine though, yeah?
Yes.
Okay.
Yes, once we fix these two things, the DAG is determined. Yeah, I'm not giving it a name because I'm gonna give it another thing a name. But this is like the starter DAG to think about. This is like, you know, because this thing makes sense. I mean, it like you can think of a content for essentially any reasonable model of computation. Like there's stuff from the past you wrote that you're now reading, there's a program counter and so on. So like this thing makes sense for anything. It won't have necessarily the same structure as, you know, as a multitape Turing machine, but it makes sense for anything. So then, so then you want to know how many pebbles to pebble, like, you know, all the things. Okay. And Hopcroft Paul Valiant showed that you can get away, so for an n node DAG, you can get away with n over log in pebbles, okay? So this strongly suggests that, okay, you should be able to get some space simulation, right? But where do we put this DAG, right? As Heinlein pointed out, this DAG depends on the machine and the input, right? This is, and there's no like obvious way to sort of like write down this DAG, right? So like if we write it down, I mean, that could, like if we do it in the most naive way, that could take like tlogt bits, could take more bits to write down a t-node DAG, right? So that's annoying, but the graph is big. But the second thing that Hopcroft, Paul, and Diane do, which is significant for us, is they think of a way to sort of compress this DAG. And this is where we use sort of locality of tape storage. And it does extend to multi-dimensions, but it doesn't, as far as we know, it doesn't quite extend to like random access, like where you can have random access storage. So I think of some way to compress this DAG. And now this, but maybe before I move on to that, I want to say that like on time versus space part 2 and 3 actually give a way to do this simulation pebbling without storing the DAG. I mean, effectively what they do is they say, here are a few ways to, you know, simulate this time-bounded machine with low space. Okay, there's like 3 different ways or something. And if any of them run out of space, just cancel that one. Okay, and then they argue in the analysis that you are pebbling this DAG here. You're not storing this DAG, but you are effectively pebbling this thing, so it works. Yeah. But so the way that the later work went was to actually think of this DAG, but like not store it, but somehow like implicitly like do what you want to do here. Yeah.
So are there lower bounds for this value,
Yes.
for this kind of DAG?
Yes, yes, thank you. Like, I think the first to note this was Paul, Karajan, and Saloni, shortly after, like maybe, so this was like 75, this was like maybe 77, they showed an log n lower bound, right? So, and
For this family of DAG or in general?
in general, but also for like families of DAGs that are literally like they're modeled by Turing, like that have like structure of multi-tape Turing machines. So yeah, so this is one of the major reasons why people thought the simulation cannot be improved, because this sort of pebbling approach where you're always writing new content into blank space, there is a sense in which that can't, like, it just cannot do
Is
better.
this thing the same as connectivity or has anything to do?
Connectivity? I don't, not really. I mean, it's a good question, but it's a little more sophisticated than that. It's a little stronger type of thing, because like, I need to sort of keep track of enough stuff to always get all the predecessors of each node, right?
So I see, so, okay, so if you only use connectivity, I believe you cannot derive such bound. So you use something stronger than that.
Yeah, yeah, I
Like
could,
vertex connectivity.
I could
like-
talk a little bit more about what you can do, like how this sort of thing would do, but I didn't plan on it, because I wanted to talk about how to get square root instead.
Okay, yeah.
Yeah. Good. Yeah, so the way we're going to compress this thing. Right, myself, okay. The way we're going to compress this thing, I guess I compressed, yeah, is to like take the time and group them together into intervals, and then take the actual space, the cells, and group them together into blocks, okay? So we'll group cells into contiguous blocks, and time steps into intervals. All right, so like, just to give some picture, we'll have some parameter b, which we'll think of as the block length and the interval length. So this will be the length of a block and an interval. So we imagine like, you just partition this thing into B blocks, B cells. There's like a block 1, 2, and 3, and we do this for all the tapes. Some group of B cells. Yeah. So we're sort of smushing cells together into these supercells, smushing contiguous time steps, like so. Every B steps here will be sort of grouped into a single interval. And the idea is like in the end, we'll think of B as about square root of T. You know, this was a special case where like B equals 1, but like for us, like we'll have B equals the square root of T. So, right, so now we define this thing, we'll call it like G sub mx is our DAG. It will have nodes 0, 1 through, let's say, roughly T over B. We think of B as divided T. And so its content will again be the initial configuration. Content of I will be sort of all the information computed in interval I. So it's like the content of all blocks, all tape blocks like accessed at the, like say at the end of interval I. State at end of interval I. So, and like whether the heads are, you know, which direction the heads are moving.
But what do you mean by access at the end of the interval?
So-
Not just of the whole interval.
So it's like the content at the end of interval I of all the blocks accessed. Does that help?
Of all the blocks.
So
accessed
there's a
during
bunch
interval
of blocks accessed during interval I want their content at the end of interval I. Yeah.
Sorry.
Yeah.
You're saying a bunch of them, but like
Still a constant number. It was-
you're still moving like one step at a time in every, so it's like 2 blocks or?
Yes, and most 2 blocks are ever accessed for each tape in an interval, right? So
Right.
this is why I said, so like it could be like at most this, right, for B steps, right? Right, they could be like this, so, yeah, so like I could have, like, that's why I'm setting the block length and the interval length to be the same. Okay, so like, you know, I'll go back and forth maybe here, but I'm not gonna go over to the third one, like I can't, like these are B cells, it takes B steps to cross all the way over. So for each of these, there'll be some blocks that I access, right? And I'll need all of those, I'll need edges coming from all of those to get my content, yes.
So previously in the definition, this I is like time step, like the I.
Yeah.
And here, it's also like the I's block, like interval time.
Yeah, it's the index of the interval, like the ith interval.
Okay.
Yeah, so right, so it covers some b steps of time. Yeah. Right, and so, right, I'll have an edge, if and only if I need content I to, get to compute content of J. I mean, in the natural, and then this in the natural way, the same way as before. So I still will have like a chain. I still need the state at the end of an interval to pick up where I left off at the start of an interval. So I'll still have this sort of thing. But yeah, if I go off to some block and then come back to some block later, I will have some edge saying, if from I to j, if I visited a certain block in interval I and I never visit again until interval j. So it's the same kind of.
And I mean, visually, it's really like making a supernode out of.
Exactly, it's exactly like making a supernodes out of the cells and out of the time, like simultaneously, yeah. Absolutely. Yeah, so.
So you have k tapes, then
Yes.
the degree, like the incoming degree will be k plus 1.
It's gonna be at most 2k plus 1. Because these could possibly been last accessed in 2 different time intervals. That's right, so there's like 2 here, in the worst case, it's like 2 here, 2 here, 2 here, 2 here, and then maybe another one for the state.
Okay, but for that, if you don't do this block partition and interval partition, is that like k plus 1?
Yeah, that will be k plus 1. But for me, right, it will be 2k plus 1 because of these 2. I mean, some constant.
I see.
Yeah, so it's like, at most 2 blocks access for each tape, and they could have been accessed in like different time intervals. And then I'll put like 1 more in there, because like, for the previous place I just came from.
For 2-dimensional tapes, I guess the integrate is something like 4k plus 1.
Yeah, it could be larger. Yep. Yeah, this is why I was saying, I think there's some hidden dependence on D in it. Yeah. Right. And I guess like another thing I want to say is that if we think about like what's happening at each node, so we're given like all in neighbors content for I, so in other words, like given, maybe I should say for J, given like content I for all I such that ij is an edge, then I can compute content of J in order B time. Okay, so because each of them will be like order B bit strings encoding like the content of blocks, I'm supposed to simulate this Turing machine for B steps. And the claim is that I can do that in order time. So this is just saying I can simulate a time interval in time proportional to the length of the end. That's okay. So now we want to pebble T over B. Right? We want to pebble the last node. Okay. Given that like each pebbling move might cost me order B space, like each particular pebbling move. And so it's not like a constant time choice anymore. Right, and so this Hopcroft-Paul volume strategy, it can be described in low space. And the idea is that if I apply it here, then, so let's say that this is my T over B nodes. So then I know that I can pebble this graph, and it will have order T over B divided by log T over B of pebbles on it at any point in time. Now, each pebble costs me order B space to hold in memory, right there, because the content being computed is order B, this little constant number of B cell blocks. So this will be T over log T over B. And right, for B, like, which is like T to the delta or some constant delta, this will be T over log T space. Okay. So this is how they managed to do it. Now, right, I still don't know this DAG, even though it's smaller, but because it's smaller now, if B is about square root of T, this is only about square root of T nodes. So what I can do is just enumerate over all possible choices of the DAG for one. And carry out the simulation. When I reach some node, I like check like, oh, like, do I really need these? Like, do I have all of the content that I need? And if I don't have, if you know, I know what I'm going to need, like at any particular point. And if there's something that I need but don't have, I just reject the graph and I try the next graph. So I can just enumerate over all of the graphs, and that's low overhead because it's only like square root T polylog T or something, like space to hold that thing. I mean, there's more sophisticated things you can do, like the later work shows you don't even need to store that thing.
So to get T over log T, why do you need to do this partitioning? Like it seems like you just do with B equals 1 and use the n over log n result. Right?
Oh, because
Why do you need log?
because I can't store the whole T node graph easily in memory without any other assumptions on the DAG, right?
Oh, I see. So that's
So this is being I'm enumerating over all of these, and these are square root, like order square root T node graphs.
so there are like additive space costs.
They just cost me like square root T polylog T extra space to store this thing. And now that I've got it stored, I can start pebbling it.
Okay.
Yeah.
Is this result about pebbling the basic one? Like, is that some graph theoretic statement about just any DAG with constant degree? Yeah.
Yep.
Okay.
Yep. Yeah. Yep. So, okay. Yeah, so that's how that works. Well, at least without describing to you how to pebble, because I want to describe to you other things instead. Okay, so I'll get rid of that.
So what's the space complexity of computing this pebbling? Is it like?
Oh, I mean, it can be done, in space basically proportional to it certainly can be done in space proportional to the DAG itself, which is enough for this. I think it can be done more space efficiently. I'd have to start writing down a pebbling algorithm to tell you.
Yeah, just one more question about the lower bound, like,
Yeah.
is it just the expander graph? Does that?
I don't think it's like, I don't think they have a very succinct description,
Oh,
but yeah.
First and second directed analog of expanders to begin with, right?
Yeah, it has to be directed.
yeah, like
But-
say you just assign a topological, some order of it, and you make it directed. Is that
Yeah.
because the vertex capacity is large?
It wouldn't surprise me if something like that could work. Yeah, I mean,
Okay, I guess at that time people didn't know expander well enough. That's like before 80s.
what's it?
It was like 70s, so I guess people at that time didn't know expander well enough.
I mean, I think they did, I think some proto-expander notion is used, like super concentrator type thing is used somewhere in the construction. Yeah. Okay,
But, yeah, maybe, thinking of the tree, how do did you call it? When the tape has a tree structure?
Tree, tree computer or tree storage or whatever, yeah.
So this won't work there, right?
Oh, yeah, like, so compressing into super nodes.
Yeah.
Yeah, so, yeah, what happens? That's a good question. So what happens is that, if I start looking at a random access, storage and I start trying to do this thing. Yeah, I don't keep maintaining the constant in degree. But like if I have B steps, I can say that the in degree is at most B, or let's say 2B, let's say it reads 2 registers or something. It's supposed to order B, right? If I read a constant number of registers in each step. So I can bound the n degree. I just, but I'm not sure how to necessarily reason about this. So I have T over B. But now, okay, right, I have T over B nodes. There's n degree order B. So, right, I basically have an edge for every step. So, right, so even though I have compressed it, like there's still like T edges. And so I didn't actually compress it if I'm trying to write it down. So that's what, yeah, that's an issue. But if I can somehow access this thing, then there is a modification of like the tree evaluation algorithm, which will get you T to the 2/3. Like if there were a way to like access this thing, like without writing it down. Like this particular thing, like by balancing like the in degree versus the depth of the thing. Yeah.
I mean, a trick like that with like going over all possible graphs.
But going over all possible graphs won't work because there's like, because I've got T edges to write down, like for each one of these, yeah. But yeah, so exactly, so I would need to somehow have a way to like access it at any point in time with like low space somehow. Like if it were an oblivious RAM, then I could just do it, right? Like so, but yeah. Yeah, so how am I doing so far?
Good for a break now, let's see, 11:30, do you want?
Okay, sure, yeah.
So how did they handle the degree issue, the tree computing over SAM? Like how did they get?
Oh. Yeah, so the way it worked in the tree computer sense, they didn't write down the graph at all. They just gave some simulation, some way to think about simulating a time-bounded computation, and then like a recursive simulation, and argued that we are pebbling this deck.
But I saw the pebbling result only works for constant degree graphs.
Yeah, well, it is constant degree if I lay it out for T nodes. Like, it's only when I compress it that the in degree goes up, right? It's only because I'm trying to handle a whole interval of B steps that I have in degree 2B. If I was handling just one step, then I'd only need 2.
Oh, I see. So they didn't like.
Yeah, they didn't compress at all. Yeah, that's why I was saying, so like, that's why I introduced the original DAG to start, because like that DAG, it unifies like all 3 papers in a certain sense. But it's the case of B equals 1. Yeah. Yeah, but we would like to somehow handle something like this, but we can't write it down. We have to do something else. Yeah. Okay, so towards getting lower space, we will look at this so-called tree evaluation problem, which was introduced. This will write down all the people. I think. Yeah, so depending on which version you read, either Mark is like first or Mark is like at the end or something. I don't know. Anyway, it's Braverman, Cook, McKenzie, Santanam, and Ware. And they introduced this problem as a candidate problem for separating P and log space. So for us, we'll say we'll have some parameters D, B, and H. Now think of B as a block length. Okay, it will be this like morally the same kind of B. Like, or a block length or like a group of bits. Okay. This will be the like arity or number of children. of my tree. So that number of children for each node or upper bound on it. Of the tree, and this h will be the height of the tree. Okay, so I'm going to have like a tree that has every node has at most d children. The height will be h. So I'm going to put functions on each of the inner nodes. So I'll have like function f sub epsilon for the root, like say f1 through fd for the children of that, going all the way down. And on the leaves, I'll put values. Okay, so I'll put like a value for like going all the way down. I'll trace a path like 1, 1, 1, 1, 1 onto d, followed by a bunch of like h1s. And these will all be b-bit strings. So we'll have a bunch of values at my leaves. So this will be HDs, bunch of b-bit values at my leaves, and these functions that take in d times b-bit values and output a b-bit value. Okay. So, I'll write that. So each of these will have, will take in d of these b-bit values and output another b-bit value. Okay. So I have these values, these sort of blocks, and I have some functions. They're specified just completely by giving you a big table. I just give you a big table for each of these nodes. Okay. And right, of course, like the way I define like the value of some inner node is like just it's the function on that node applied to the values of the children. I guess for simplicity, I'm just going to assume that they all the inner nodes have exactly d children. And this is sort of easy to modify if they have a smaller number. Okay. So it's some sort of formula evaluation where at very complicated gates, you think of d as maybe 2, taking in a b-bit block here, a b-bit block here, and computing some new b-bit value. So I'm passing these b-bits on the wires. Okay, and then the task is, the goal here is to find the value of the root. Okay. And we want to know how much space this takes. Is the problem clear?
So how is this tree specified?
Oh, it's just completely given as part of the input.
Okay.
Yeah, and the way that these guys are thinking about it, like this entire thing is given the input. So we think of h, sort of input length as n. We think of h is about like log n. We think of these tables, think of b is about like order log n, right? And then d is like a constant. So like it's all like input length order n. Okay. Yeah, that's the way they thought about it. We're not going to think of that, but that's the way. That's part of like the mental jump from going to this to that over there. But yeah, so we want to know how much space it takes. And there is, a pretty easy DFS depth first search algorithm, which will take us h times order h times d times b space. Okay, and right, the idea is that at every level of the tree, right, if I sort of just start with, the ones down here, like all of the children here, and, just individually pebble, like the minimum number of nodes I need at every single level, and if I'm just doing a pebbling argument, I'll need it like at most d minus 1 at each level of the tree at any point in time. Like so, because like there's always maybe one last one I'm trying to compute. Once I've computed all of the d children, I can compute the next one, erase all of these, and continue. So I never need more than like d minus 1 at any point in time. Like once I get the d, compute the function, get this one, erase the others. Okay. So so just using like a sort of depth first, very degree racing. So we can think of this as pebbling a tree of this height, and right, it will take h times d pebbles, and each pebble costs me order v bits. Okay. Right, and Graverman, Cook, McKenzie, Santana Bear looked at pebbling and generalizations of pebbling and showed that effectively this DFS is about the best you can do in like lots of cases, even some generalizations of pebbling. So this is why it was a big surprise when Cook, the other Cook, this is S Cook and this is J Cook. Revenge, I like to say Revenge of the Sun or something. And Mertz showed that in fact this thing is a much more space efficient algorithm. So they show you can get h times log of dB plus b space. Okay, and so if we think about it in terms of the original, this is given as an input of length n, these functions are given as an input of length n, they get in order log n times log n space algorithm. That's why their paper is called tree evaluation space log n times log n. So yeah, I guess the main thing to remark here is that we're taking this should be d times. We're taking this thing which is like, so if we think of d as a constant, we're taking things as the product of these two things and almost replacing it with the sum. So it's maybe natural that the square root could come if you could use it for some other problem. I mean, I could give you some of the key ideas now, or I could just literally give you the algorithm. So I think I'll be able to just give you the algorithm. I think. How much time do I actually have?
You have however much you need.
Okay, all right. So okay. Until well, at some point we might be starving, and then we'll. Yeah, but
Yeah, I'll put it on you.
you'll put it on me. Yeah, it'll be all on me. I'll try to at least keep it entertaining. But yeah.
You're doing a good job so far.
Thank you. Okay, I'll try. Yeah, let's see. Yeah, so, okay, maybe, I will choose the rest of your lecture, so I'm not entirely responsible. But, we can, you can choose the best lecture. So I could immediately start telling you about the Cook and Mertz algorithm. Or I could tell you how we use it, how it gets applied to the DAG. The Hopcroft-Ball value DAG.
We're gonna do both in the end, or only one?
We will see, I guess. Which one do you like? Which one would you prefer that we do? Like, would you really want to?
For me, the algorithm itself.
The algorithm itself?
Last time you were here, you showed how it was applied, but didn't show the.
I did not, I was not able to, yes.
Yeah, so let's
All right,
do the
all right.
algorithm. Although not everyone was here last time, but.
Yeah.
There are at least videos on that, I suppose.
Exactly.
Yeah, okay, great. So we'll do the Cook and Mertz algorithm first, okay? Okay, so the first thing I'll do is I'll simplify things a bit. I have notes on how to undo the simplifications if you want, but actually for us, we really do just need the degree is constant. I mean, we are essentially going to take, like the way we map space efficient evaluation into this is we take our T over B node compressed DAG and sort of unroll it so that if we had in degree in our DAG like constant, the number of children we have for any particular node is constant. So I'll say that this is constant, and we're going to go for something slightly weaker. I will sketch how to do better at the end. So instead of getting a pure like order B, so I'm thinking of D as constant, so I'm gonna leave it out. Instead of getting like a pure like D times B, I'm gonna get B times log B. Yes,
So regarding the space use, are you allowed to change the space occupied by the inputs?
no, you're not allowed to change the space occupied by the input. No, that you could do it in, probably do it in constant space.
Yes.
Yeah, I mean, depending on how you wrote the input down. Yeah. Yeah, in most of these space bounded models where we're looking at sublinear space, we are not allowed to touch the input. Yeah. It's only we only get additional space. Yep. Another thing is actually we can assume it all generally that D is just 2. That will make the algorithm much easier to write down. And so, yeah, what's the idea? So let's say I've got some constant arity. So I've got some constant arity thing. It's got D here, and I've got like some x1 through xd, they're all b-bit strings. Then what I can do is basically replace this with like something of log of D depth, like a log of D depth binary tree. So I'll increase my block length to something like, so I'll increase B to like D over 2 times B. And then, right, so that way my last node can take in like the first half, x1 through xd over 2, and the second half, xd over 2 plus 1, xd, and then compute the answer. And so I guess to slightly expand the block length, and now I can just have like a binary tree. And I'll just have some special node M for merge, which is like maybe take some padded version of like a quarter of the inputs, a padded version of a quarter of the inputs, and then merges them into something like this. Okay. So like I can easily make D equals 2 by just sort of adding this, but I do make the height a bit longer, but it's a constant, so it's a log of a constant, so we really don't care. Yeah. So we can think of it as just 2, and that will be very helpful, and at least for writing this thing down. Okay, so we're going to work over a field of characteristic of 2. So the order of this field will be some 2 to the q, where q is at least 2b squared. We'll think of it as, let's say, you can think of it as something like theta b cubed. Just something big enough, but not too big. And then so for all of the nodes in our tree, U, and all possible output bits of a function, so J1 through V, we'll define F Uj to take in 2B bits. So this is like just outputting the jth bit of Fu. Okay. So we'll just sort of break Fu's output into like these single bit output functions. And then doing that, we'll define the multilinear extension of that in a natural way. So we'll have like 2 groups of B variables, x1 and x2. So we'll have 2 B variables in total. And our multilinear extension is just going to sum over all the possible values of it going into the input, and take like the characteristic polynomial, which on x1, x2 outputs 1, if and only if the input is equal to a1, a2, and 0 otherwise. And we'll multiply that by Fuj on a1, a2. It's a standard multilinear extension. I'm just writing it down so that, because we will refer to like oh, can we space efficiently compute this? And the answer is yes, we can. So we're just polynomializing each of these functions, fu, and we're doing so by like breaking them up into b different functions, one for each output bit, and then like defining a polynomial which agrees with it on all Boolean values. Okay. So in particular, we have f. Sorry, almost lost my iPad. Thanks, yeah. Here we have fu1 on u0 u1 concatenating with f ub the value on u0 and the value on u1. This is just the value on u. Okay, so this is just taking like all this notation and saying that on Boolean values, so like these are the values of, we have some node u, we have u0, u1. We take their two values, we evaluate them on these b polynomials. Each one gives us a bit, that gives us the value.
Just to understand the type, so f
Yeah.
tilde, what is its domain?
Yeah, it's a polynomial. So it
goes
takes,
from f squared to f?
yeah, it goes from, so it goes from f to b
To b, okay.
to f, each of these. And we have b of them. Yeah, so we can certainly think of them as functions in this. All right, this time. Yeah, so this is actually why we're getting this b log b factory. Because it's multilinear extension business. Because we've got like two b variables over a field of poly b. I'm just sort of saying that out. Because if you use the low degree extension instead, like something like a little more compact, use order b over log b variables, you would get rid of this, you would get the Cook Mertz algorithm. But I'm just using multilinear extension because it's like easier to think about. It's like, it's a little more complicated, and we can do low degree extensions in our own timeline. We know those things, okay? So, yeah, so the key fact, okay, I don't want to write it over there. Okay, I'll write it here. So the key fact is, okay, suppose I have omega, which is a generator of a multiplicative subgroup. So it's a generator of f without 0. And right, you also think of it as a primitive mth root of unity. If I give you A1 and A2 and B1 and B2, which are all B vectors from the field, they're all in F to the B. And if I give you any polynomial P of degree less than m and 2b variables, then the following equation holds. Basically a polynomial interpolation trick. I realize I have a line going right through my key. All right, it's fine. Yeah, so basically just a polynomial interpolation, but it's extremely fundamental. It is the reason why this thing works. So suppose I want the value of P. Think of P as one of these, right? So P is really supposed to be one of these F tildes. I want the value of P on B1, B2. That's what I really want. But I don't have that. Somebody messed up my storage space and they gave me A1, A2 instead. Yeah, but I want to compute it on this one. So what I will do is I will sum over all I from 1 to m. And I'll evaluate P on omega that I times the storage I've got. And I'll somehow be able to add in B1. And I'll multiply this storage I've got, and I'll add in B2. Okay, so I want to compute it on B1, B2, but somehow my storage, I'm really greedy with my storage, and so this is what I want, and these are what I have. And I don't want to use any more storage to compute it, right? Like I don't want to pebble. I don't want to use new, I don't want to write my value into new space. I want to XOR my value into existing space. This is so I don't want to take this value and write it into blank space. I want to somehow just add it in to something. Okay. So think of this as the memory that I currently have, and then I want to get the value of this. And so I'm going to somehow do that by computing some running sum over, this is poly B values of this polynomial instead. And by magic cancellation modulo 2, it will give me this value. Okay. So this is what I want, and this is what my algorithm will try to compute.
So this only works for characteristic 2?
Oh, no, you can totally use it in higher characteristics. It's just now, in characteristic 2, I don't have to worry about subtracting or anything like that.
Okay,
It's just cleaner in characteristic 2.
Okay.
There's nothing, there is an analog of polynomial interpolation in any. It's just a form of polynomial interpolation.
And they all work to give the improved.
You could use them, yeah, you could use any of them. Yeah, I just use characteristic 2 because I can leave out a minus sign and stuff. Yeah, it's but it really is a polynomial interpolation trick, okay? So this is so we'll stare that out. Right, so I'll erase this thing. Right, this is what we're not going for this, we're going for that instead. Because we're using multilinear extensions.
So I mean, geometrically, we're used to thinking of it as if you have some line and you read the polynomial on a point by reading the values of the rest of the line.
Yeah,
So far, that's all I understand from this, and
yeah. I mean, this comes up so many times in showing worst case to average case reductions.
Right.
So I like to think of this as a worst case to arbitrary case type reduction. So I've got this arbitrary storage I cannot control. I want to somehow reuse it to compute a value I do want to control.
okay, but what's but I don't understand what's the difference between, what is the have? I mean.
Yeah.
Which A1s are you gonna be using it with?
It will be any. So the universal quantifier is over any. So yeah, it will be clear in the algorithm, but right now, this is probably mysterious, but the algorithm will literally implement this. And you will see there'll be a for loop over I and everything. I'll be multiplying by omega to the I, it's a weird implementation of this that's space efficient, maybe is the way to think about it. Because I'm still going to compute all these function values, but instead of writing them into a new blank register, I'm going to XOR them into some register. And I'm going to recursively assume I can XOR the value of my 2 children into registers. And so because these are the values I want the values of my children to compute the function I want. But okay, so first, before I say the actual algorithm, I think it may be easier to say what the space usage is going to look like. So the previous algorithm, right, is that first thing, it had height h and it was storing up to d times b bits in every layer of the tree. Right? So here our stack space will have order log b bits at every layer, which is height. And that will literally be storing a value I. It will store an I in a running sum. So these will be storing I's, okay? And I'm going to do it for the the height of the tree. And I'll have that, and I'll, instead of having separate space storing these intermediate values at every level, I'll have a global space that's storing just, I mean, most of the time it's just gonna look like garbage, but it's going to be XORing the values of children and everything I've ever computed in here, like as I'm going. So, but it will have like the node name, the name of the current node I'm at. That'll be order H bits to write down. And it's just sort of tracing a path from the root to the current node I'm at. And it will have a register X1, which we think of as B, I'll just say it's an element of F to the B. X2, element of F to the B. This is where I get the order B log B bits, and another Y, also an F to B. Okay. And so my total space will, if that's what my space looks like, it will be like this. H, this is the stack space, and then this is the global space. And so I'll have order B log B bits to write down each of these. And this is just takes order H. Okay, so that's what the space usage will look like. It will not look like this one, so let me just go ahead and erase it right now. So somehow I'm going to aggressively just reuse space over and over at every level of recursion. Okay, so I'll have an algorithm that I'll call add.
So,
Yes,
right, when you
yes.
said this stores eyes,
Mhm.
you mean it stores like the path?
It stores the index I in a running sum to compute this.
Okay.
So like, let's say I'm trying to compute this function at this particular level,
In the.
like in the tree. Yeah, I'm at some node, I want to compute this function, right? But in order to compute this function, I've got to, I want to compute this running sum. So I store like the I that I'm currently computing I'm going
Then
to
you need
compute.
to go somewhere else in the tree, and that's why it's a stack of eyes.
Yeah, it's a stack of I's because every time I want to compute the sum, I've got to call my children to figure out B1 and B2.
Right.
B1 and B2 are like the values of the values of these two. Right, so that's what will get added. So I have to call, your recursive call to add these in, and then compute this polynomial, and then add that into some running register, and then increment I.
Okay.
Yeah, but I'm basically describing the algorithm before I wrote it down, but yeah, it will also be there, yeah. Yeah. That's fine. Yeah, so this algorithm add is going, so we'll just see what it does to the global space. So it's going to map U, like a node name. So we think of this as the name of a node, like starting from the root, like tell me 1 through D, like a path. So it's going to map U and these three registers to U without changing X1 and X2, but it will XOR the value of U into Y. So that's what I want. Okay, I want a recursive procedure that will take a global storage something like this and make it look like that. Okay, so initially, I will say I have an empty stack, and global will just be, I have epsilon, that's this index of the root. I want the value of the root, and I'll just set, X, Y, X1, X2, and Y to all zeros, okay? Right, if I can run add and it will have this behavior, it will just add the value of the root here, and I will be done, okay? All right, so, right, so I think I can put it, I can just put it here and then it'll be good. Okay, so I'm given this storage, Ux1, X2, Y. So first of all, right, if U is a leaf, then I just simply return the answer, okay? Because in the tree evaluation input, I'm like, the leaf is just right there in the input. So I can just add it in and be done. So we're going to return that with Y plus the value. Okay. And, you know, if I'm simulating a multi-tape Turing machine, a leaf corresponds to a source in my original DAG. So that just corresponds to returning the initial configuration, which I can always compute. Okay, so I mean, I'll make these analogies as I go, so that this will be easy. So leaf case is trivial. Now, I'm going to literally implement this equation. So for all I ranging from 1 to m, okay, I'm going to compute this sum. So I'm going to call recursively. So this is add. Should give my thing a name. Call add on the left child of u with x2, y, and omega to the I times x1. Okay? And recursively, what will this produce? Let's see.
Wait, why is only 3 stops? We don't need 4.
Sorry?
There's a 4 tuple in, like why this is?
Yeah, this is 4. This is 4. This is 4.
Oh,
This is 4.
that's 4?
Y comma,
That's a comma.
Oh.
Comma. Yeah, so I rotated things, and now I'm calling on this. What is that gonna do? It's gonna add this plus the value on U0, right? And everything else will remain unchanged. Like, according to this, right? Like inductively, I'm gonna maintain this assumption, okay? So it will add that, all right? Let me give this a name, yeah.
slower, I don't see how this is that, so.
Yeah, it's okay. I'm gonna, so that should be x1. Oh, I'm just saying that, this add has a property that if I give you a node name, and I give you any 2 registers and a third, this thing will and when it gives a callback, it's gonna add the value of u into the third register. All right, so here I'm telling you, tell me the value of my left child with this register, and this one. So it's going to add the value of the left child into the third register.
Oh, wait, you cannot say that omega to the I times x1 is a register, so I'm guessing you are passing down some
What do you mean?
omega
No, I'm going to multiply.
Mm.
So I mean, I multiply omega to the I in, you know, in x, like with x1. I mean, so the idea is I start with this input, right? I multiply omega to the I, like for I equals 100, I multiply omega to the I, and I rotate the registers around, so they look like this.
Also, you're actually doing like first x1 becomes x1 times omega to the I.
Yeah, I'm not
and then
writing
you
like
call-
every single little step because it would fill up this whole board.
Yeah.
Yeah, so I am compressing some steps, so just keep asking questions, like, there's nothing, I'm just implementing this, like, but in a weird, like,
So
recursive
now I
way.
see that add is weird, because it doesn't seem to need x1 and x2, you're just kind of stressing that they're still there.
It has to work really hard to put x1 and x2 back the
Back.
way they were.
Right.
It actually is gonna use x1 and x2 aggressively, and then put them back the way they were. Yeah. It doesn't seem to use them, but it's important it leaves them untouched so that later levels of recursion will be able to maintain this property, right? Because A1 and A2 change, this thing doesn't work anymore. Yeah, from one value of I to the next. So
Oh, I see.
yeah. So I need the A1 and A2 to be the same, like for all I from 1 to m. Yeah.
So far, are there any additional local variables that the program has introduced?
I mean, nothing more, I mean, nothing really other than I and like, you know, something holding omega to the I, which is being multiplied by, but like, let's just order log b bits. Okay. Yeah.
So if D is larger than the 2, then you probably need the few registers to store.
Yeah, you'll need D registers here. You would want D registers here. Yeah. So that, and then obviously makes it even more complicated. That's why I made D equal to, yeah. Okay, so this is just basically processing the left child so that it will look like, you know, I will get this value that I want. And then I'm gonna call add on U1. Now, so I call this like X prime one, so I still have this thing just rotated around. Y,
So it's still the register X1, it's just the value is different.
what's that?
It's still.
Right now, it's different, yeah. I promise when the thing ends, it will be what it was before.
It does.
I'm still running the algorithm,
but
yes.
It's
What?
the same register, right?
This register has a different value, which is X prime one. It will be reset to X at one at the end. Yeah, yeah. And so, okay, so then, inductively, this will give us this X prime one, Y, and W to I X2 plus, VU1, right? It will give me the right child now, because now I'm asking for the right child.
So the left and right child play the roles of B1 and B2.
Exactly, yes. Yes. Yeah, so like, the point is, these are the values I want, the children, and these A1, A2 are the values I have. And I'm sort of multiplying by omega to the I, and then recursively adding in the values I want to get what I want. But like, I haven't evaluated the polynomial yet, so I need to do that. But that's the very next step. So let me try to.
Right. This is a silly question,
Yeah,
but like instead of permuting things, can
Yeah.
you just think about, you have 3 add maps where every time you can also just choose which value gets added, right?
yeah, I could do that too. I could have like an index saying add into this register, add into
Right,
this.
it's the same.
I could do something like that, yeah. There's,
Just easier for me to kind of.
sure, yeah, I mean, whatever helps. I could keep writing here, or I could just, maybe I'll continue the algorithm here. I don't know. It'll be a little bit easier.
Space efficient.
Yeah, I'm trying. So now I'm gonna compute the polynomial. I'm gonna compute the value of the function. I'm gonna compute this right-hand side. So far, I've set up these values here. I've set up these inputs. They're sitting in 2 registers. They're exactly this X prime 1, X prime 2. Now I'm gonna actually compute P. This is inside of this for loop. So I should be indenting this, okay? Because so this is inside the for loop, for all. For I, okay. All right, so for this, I'm gonna compute my F hat or F tilde uj on X prime 1, X prime 2. Now for this, I will use order B extra space. Okay, so I will enumerate over all the values of A1, A2. I will evaluate this characteristic polynomial. And then I will look up the value of this and either include, like, so this is just a bit, right? So it will either include in the sum or not.
So this you're doing straightforward, no trick.
Yeah, that's just multilinear extension evaluation, yeah. So this will just be, or use it differently. This is just order B space. Do that. Yep, and then I will update my register Y, right, which is the one thing I haven't changed yet. I changed the X1 and X2, now I have the Y. So I'll update Y to be Y plus the concatenation of all these things. So FU1 on X prime 1, X prime 2 through FU B on X prime 1, X prime 2. So I'm just concatenating these B bit values and adding them into this running sum Y. Okay. So now I'm doing this over all I. Okay. So, but before I get out of this loop, I want to change X prime prime 1 and X prime 2 back to so I'll just say change X prime 1 and X prime 2 back. Okay.
This is just
By this, I will do another recursive call. I'll call add again, right? But mod 2 will cancel them. So I'll call add again to add this and cancel it. collide again, add it and cancel, now divide by omega to the I.
And you could have done subtract if you weren't either.
I could have just done that, so, right, and so now that will get me back to some u, x1, x2, y prime. And then the claim is that by this formula, star, when I'm out of this for loop, y prime will actually equal the value that I want. So the y prime will equal the value of u. Okay. Value of u. Okay.
How does any of this depend on the left-hand side? How does that depend on I?
How does what?
How does this computation depend on I?
This computation, yeah, it depends on I in a subtle way, because like this x prime one is actually w to the I times x1 plus this thing.
Why can't I just do all of that first and then do this?
What do you mean do all of that first? I
So
would
just
need
add
space for each of those.
W1 times x1, W2 times x2, x1 and so on, and then do the left-hand side.
I'm only allocated space for like one of these at a time. Okay. I'm doing a recursive call every time, like to do an add, which is storing like the current value of I that I'm at. Right, so I don't need recursion for this thing, right? I just need recursion to like compute the sort of inputs I need.
It's to save space, saving the I.
It's to save like space, like crazy to save space. I'm just gonna reuse the same stuff over and over and over again. Yeah, so this just takes order B space, and I'm adding this into some running sum. And by this equation, this running sum equals the value that I want.
Who is A1 in this?
A1 is x1. And A2 is x2. Yeah, I guess I didn't want, like, I'm thinking of those as variables, and over here I'm thinking of as field elements, so that's why I can.
Sure.
But see, the point is at any point in time, anywhere I am in the algorithm,
Right.
I've got an x1, x2, which I can't control.
Right, so that's the thing. You have some x1, x2, that's like memory from other, you don't care about it right now.
Yeah,
You're stuck with them.
yeah,
So you're doing some omega to the I multiplication on them, and then they disappear.
yeah.
And you get back your B.
Yeah, adding in the values that I want. But where, you know, I really want to compute this polynomial. And I can recursively like add in these values, but I can't just compute this right out. So it's like an extremely indirect way of doing it by reusing the space I've got. And, you know, taking some big sum, which so like I need to keep track of I for to track these recursive calls. Yeah, yeah, so then now I'll just return what I've got, like when I'm at the end, like, because that's. Oh, so it should be this should be y plus the value, right? Because that's what I should be getting, y plus the value.
So this change is after the for loop, for I loop.
Yeah, it's after this loop. Yeah, it's after this loop. I change them back before I go to the next thing.
And this.
Yeah, because I need x1, x2. I need the A1 to be the same for all values of I. So I need to change the x1 back to this thing to restart the thing.
Yes, so the only difference in the, like, you had like the first for I loop.
Mm-hmm.
And the second for I loop will be the same as the first one, except you don't do this for J loop, is it?
I'm not sure what you're saying.
Yeah,
So
so I'm just saying, like, what's the procedure in this change?
in what
It's
change?
another for I loop, that's what he's saying.
No.
The change downstairs,
Oh, this is not, no, it's just one for all I loop. It's just one of them.
how do you do this change? Don't
Yeah,
you need
what
to
do
do a recursive, like a for?
So I have this for I do these things, I compute these things, put in a running sum, and then inside of I change these things back to what they were. So I change them back to x1, x2, so that when I come back up here, x1 and x2 were what they were before. So that way I I don't necessarily need to divide omega to the I, could keep omega to the I, because I'll multiply by multiply by omega to get like omega to I plus 1 or something. But just to make it cleaner, I just reset them completely so that like because I need the same values, A1, A2 for every I in the loop. So I actually do reset them like right here so that when I come back up, I have the same X1, X2 I had before.
I see, so the change happens inside the for I loop.
Yes, 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 yeah, so this is, okay. Whoop. Like that.
Yeah.
And then this thing is also happening, the for all J is happening here too.
Yes.
Yeah.
Maybe another, oh, sorry. Maybe another, it's like a silly question, right? We're
Sure.
stressing that we're always using the same memory, right? So like when I recursively call add on whatever's there,
Yeah,
from the point of view of like add of the lower node, it is getting memory that was like used for some kind of partial computation of the higher node, but it doesn't care.
it does not care. It does not care. And sort of by the structure of the thing, every time we're calling it on a particular, value like this, or particular node name, we've got the same X1, X2. And that's important, so that way we can carry out this equation. That these two are always the same when we're making them. Yeah.
Yes.
Otherwise, they're gonna be arbitrary.
So I don't need to worry myself about like opening the recursion. I just know that the guarantee is that you get
Yeah.
everything back as usual except for.
Yeah,
the
this
last
is the key variant, to keep in mind, yeah. And you're right, and so like we have the stack which is changing, but the global space, right, has.
So what prevents you get a like log space algorithm for this? Like it is still log times log, right? Like
Yes.
Can you like further improve to L to show it and see how?
So, I mean, the main bottleneck right now is this polynomial interpolation, right? So to compute this, I apparently need to sum over something like this. Now, why do I need to sum over this? Because I need to sum over a number of terms, which is at least the degree. And the degree is like, 2b, right? So like I need to interpolate over 2b points to get the thing. That's the bottleneck. So I have to store where I am, and that's gonna be, this I, that's log b. Right? If I can make this a constant, this is the bottleneck, right? Because there is a way to like make this order b by like doing a low degree extension instead of a multilinear extension. In other words, like you think of having order b over log b variables, and now like each one of your field elements is actually encoding log b bits instead of just 1 bit. So you can shrink this to order b, but this is a bottleneck. Like we don't know how to do an interpolation with only saving a constant number of bits, like for each recursion. That's the issue. Yeah.
So the change will undo, will run the second add to get X2 back, and then run the first add to get X1 back, is it?
Yeah, exactly. So it will rerun this add and this add again to erase them, to erase these values.
Yeah, okay.
And then it will divide by omega to the I.
Yeah.
And then it'll rotate everything to get X1, X2 with like some Y prime in a running sum. And then by this equation, once we're done to the for loop, the Y prime will actually be Y plus the value we want. Because we're just adding like summands of this thing into this running sum. Yeah, there is some similarities to like quantum algorithms here, right? Like there's uncomputing, right? Like there's a massive cancellation, polynomial interpolation. Like there's I don't know. There's something else to be said about this. There's seems to be like a lot of uncomputing and cancellation.
I mean, the reversibility is inherent in it.
Yeah.
Cancellation, it's more like, to me, it's more like a code, like a decoding from any element.
Sure, yeah, you can think of like,
You want your point, B1, B2.
yeah,
You're given A1, A2, and you need to be able to interpolate in a way that uses this A1, A2.
yeah. Yeah, I mean, more importantly, you want the output of the function on B1, B2, and you can only get the output of it on like this other sorts of points, part of which is just beyond your control. Yeah.
This also reminds me that we're coding, that you have reverse, you need to decode, and you have this interpolation.
Yeah.
Similar techniques.
That's true.
Yeah, that's good. Going back to what I said before, like this kind of sort of thing is often used in like worst case to average case reductions. Like this is what you want, and like if I take like random elements or something, then I can interpolate. If I pick this sort of things at random, if I pick this at random. But like this is an even stronger property. It's like, actually, no, the universal quantifier is over A. It's not even like higher probability A1s and A2s that work. It's like every A1 and A2 that works. So it's like, that's why I was saying it's like a worst case to arbitrary case in some weird sense. So like it actually exploits even more Polynomial interpolation than what you normally see in TCS, at least, like it's actually every single value you can interpolate from.
But in this reductions, you have to do average case simply because there are some errors, right? And in some sense, this is like the error-free version, so you could.
This is like an error, it's like an error-free version, it's just exporting like the full universal quantifier over the A1s, A2s, yeah, like. Yeah, so to me, it's somehow squeezing even more out of this trick that.
You can imagine that instead of using this code, you use some code that's especially constructed for this property, this arbitrary to worst case.
Yeah, or if you use like some properties of some function, if your underlying function has like lower degree, for some reason.
So,
because the way you structured it, because the way you structured its inputs, yeah.
So if you have some code that's like worst case to best case decodable, and that only needs like much less than m many probes to decode, then you can get rid of this bottleneck of H log B.
Yeah, you could possibly, so
Is this relation also used to decode like the Efrem-Kuyakanen LDC codes?
Oh, I'm not.
No, I think this
sure.
is more like local correction instead of local decoding. Because you have to fix everything back up to where you were.
Okay, yeah, but like this same interpolation trick is also used there, right? Or something similar to it.
No, this is just like read mother. This is much more basic.
Yeah, it is like, yeah.
I mean, maybe there is a subtlety here, right? The parity check that you're using here, if you think about this as a code, is something that also has like a very succinct representation, right? Like you only need to multiply by omega to it's not.
Yes. Yeah. So that's another property I'm exploiting, is that like it's a very sort of easy interpolation formula. Yeah.
Is that really important? I mean, if you could afford one more register besides the.
Or.
I mean, if you had some other coefficients instead of omega to the I, which needed some close, but.
Yeah, I mean, as long as I only need like order B space or something to perform whatever operations I'm doing, I could do that, then erase it, and then I'll have like my x'1, x'2 true. Like there's a lot of freedom actually in doing this sort of thing, yeah. I guess it just makes the description simpler to like have a simple formula.
So it looks like we are just a good code away from tree evaluation in log space.
I don't know. No, because like I mean this is it really is like in general a polynomial of degree 2b, and if I want I'm not really sure what to.
So you could replace this equation by any parity check of the code.
Possibly. Like I really do need it to work like regardless of what A1, A2 I start with.
Right, but there are many parity checks. These are some that you are using.
Yeah, this is just one chosen to make things smooth. Yes, but you could. Right. Yeah.
You need to be able to, if the parity check involves Q queries, the first query is A1, A2.
Right. You
need to be able to compute the next query from the previous query in a way that you can then undo it.
There's a lot of like, subtle properties.
Okay, maybe we'll let you go on.
No, it's fine, No, I think we're doing, I guess it looks like it's 12:30.
We can go until 1 if you want, and we can still get lunch. We'll
I mean,
still survive.
Okay, would you like to see how you use Would you like to see a review of how like this is used?
I think so.
Yeah, fine.
If you are up for it, I mean.
I
don't want
think
to-
so, I think so. If I start like leaning too hard in one direction, then we can just go have lunch. Yeah. Yeah, sometimes, not sure, but yeah, the rest of this stuff is more, standard complexity stuff, so like how we. Or I could just tell you the open problems, I mean, I could discuss that, I don't know.
Yeah, that's good too.
Yeah,
Up to
okay,
you.
okay, yeah, maybe I'll just say that the open problems, because I feel like there's enough other videos of me describing the reduction.
You mean the reduction from this back to the square root space?
Yeah, so going from the, I guess it's, so going from like, right, we had a DAG. And it had some like T over B nodes, and they were implementing B step intervals each, right? Something like this. And like on each wire, we had some, say, B bit values, right? Like encoding a tape block, right? Some content. That we were needing to compute, because right, we had these blocks of B cells. But let's just ignore constant, just imagine this B steps and B bits, right? So this is, if we thought of tree evaluation as being evaluating B bit functions on formulas, this is a circuit evaluation where I'm evaluating B bit functions, on a DAG. Okay. So then, to get to tree evaluation, so let's just assume that we know this graph somehow, okay? And B is about square root n, so this is, square root t, so this is something stored in like square root t. So to get to tree evaluation, we just use like a folklore way of, say, if you've got a Boolean circuit, this is the case of B equals 1, a Boolean circuit of depth h, we can always translate that into a Boolean formula of depth h. And the idea is to simply sort of unroll this thing starting from the output gate. So like sort of recursively evaluate it backwards. Like imagine I am trying to evaluate this in a depth first way, right? So I can recursively call to get the value of this one, recursively call to get the value of this one, and then compute the value, right? So basically applying, imagine like what it looks like to apply the obvious depth first algorithm of like that before Cook and Mertz to a circuit, like but trying to evaluate like that, starting on the root. So then, like you will just be walking it backwards. So to get a formula, right, just means the out degree is at most 1.
So the size blows up now, but you're never going to store this, I guess.
The size blows up by a lot, right? The size will be, 2 to the order h size, right? But I'm not storing this, right? Like I have this is stored. I can refer to any node here by specifying a path here, going backwards to a node, right? So every node here is uniquely determined by telling you a path, like say here, and that would correspond to going like here and here, right? So just by telling you a path, remember it's constant n degree, so that will be constant number of bits for each node on the path. So this will be order t over b. I can specify any one of them with order t over b bits. And given this DAG, right, I could just like, if I have like a node here, I can figure out what that node is here. I can figure out what its children are in the tree by just looking at its predecessors here, right? And then having names for those, Right, so I can compute any node I want in this tree and order T over B space, given this access to this thing. Okay, and yeah, what's happening, let's say like this, like I already argued that even if it had like a large constant in degree, we could make that in degree 2. So it's just, like 2. And right, like if the values of the leaves are just the sources here for us, the initial configuration. So it's like, it'll just have initial configuration as our value here. We don't have to store that. We can always compute that anytime we want. So we just run the Cook-Mertz algorithm with this interpretation of the tree, given this DAG.
But
Yes.
so in the description of the add algorithm,
Yeah,
like where do you actually need it to be a tree? I think it just directly work for that.
yeah, as long as you can, as long as you have a way of referring to this thing, yes.
Yeah.
Yes, it's just that tree is only more powerful because like, you could have a separate function for every possible path you might take. The tree could be possibly more powerful because I get a different function for every single node.
Okay, I see.
But yes, this is true, it's true, it would work as long as I have a way of translating, so this is like my path in the DAG, and then I have a way of looking up, okay, what are my children? So every time I do that kind of call, I'm gonna like look up, okay, what are my children here, yeah, to see where I'm going. So like I'm implicitly defining some massive tree evaluation instance, assuming I have this graph. Okay, and so then, right, this is my height, and my, this is my b-bit thing, and I'm assuming d is constant. Recall that we had order db plus h log db space, right? So if our d is constant, we set b to be about square root t log t, right? So that way our height is square root of t over log t, and so we get the space bound of order t log t, square root t log t.
Where do you need multi-tapes?
I need multi-tapes in the fact that this is a compressed graph. Well, I still haven't proved the theorem. I assume we have access to this graph. And I need multi-tapes to argue that I have a compressed representation of this graph. Right? For RAMs and everything else, it's a T-node graph. Or it has T edges, right?
So it's like one tape is to store this graph, another tape is to execute this tree evaluation algorithm?
Yeah, you can think of it that way. I mean, because we only care about the space, we could put everything on one tape. It's not, because we only care about the space, we could just put everything.
Oh, I see. So
I
The
guess-
point is that a multi-tape has such a
Yes,
succinct
yes.
representation.
And we don't know whether such a representation, in fact, I mean, in a certain sense in which such a representation isn't possible for a random access machine. But yeah, so I haven't removed the assumption that we have access to this graph, but like right now, right, we can store this graph. So there's a way to store this graph in order t over b bits. We need that actually. So how do we get our hands on this graph? What we do is we just do the standard old PCS trick of guess and check. Okay, we try all possible such graphs. Now, we cannot just write down like the edges one by one, right? If it's ordered t over b nodes. So we have to be more careful. We have to use the factor dealing with a multi-tape Turing machine. But
Why can't we just write it down?
it takes log t over b bits to write down a single edge, right? Like I have to specify one edge and specify another edge.
But isn't this like t over b times log t over b?
Yeah,
So if you don't care about log factors.
if I don't care about log factors, I can do it.
Oh, okay, okay,
But I care about log. I mean, why not? Why not care about log? I mean, I wanted to get square root t.
okay.
Big open problem, okay. Yeah, so yeah, so yeah, if you don't care about log factors, then okay, fine. So what you can do instead of like explicitly writing down these edges, we use the fact that we're dealing with tapes, and So from one time interval to the next, right, our actual tape blocks will only change by, you know, some constant. So we just need to store like increment or guess increments and decrements for all like the tape block indices from each interval to another, which is just constant bits. Then given that, if I want to know if there's an edge, I just simply run a counter, taking order log t bits, to like keep track of, okay, what are the tape block indices I am when I get to here? And then what are they when I get to here, and what were they in the middle, right? If I leave one tape block and come back, you know, from I to j, and I didn't visit it in the middle, then I should put an edge. But that I can just do with log t space. I just keep just maintaining counters. So I'm just guessing how the tape blocks change. Like +1, -1 stay the same, like from one time interval to the next. And so that just takes a constant number of bits per node. And I can look up the edges in the order log t space too. Okay, so I could guess them all. So I guess this thing. And then I need to check that it works. And so what I do is for each of these possible guesses, I create a tree evaluation instance. Okay, because for each DAG, there's a different tree, right? Like based on the edges I chose. And for each one, I'll have a function, which is basically checking, you know, like any particular node, like whether, you know, because I'm telling you, I'm guessing like what the tape block positions are, like how they change. So so my functions are just going to check if anything is ever violated. Like if I ever try to access a tape block that I said I wouldn't, you know, like, you know, the tape blocks change in any way different from what I guessed, then I just output fail. I output some special fail value in my tree. And then if I ever see a fail value, I propagate it up. So I'll just output fail, like if the graph isn't what I want, if it doesn't mimic exactly the way that I want the head to be. So it'll output fail or output accept or output reject. And so that's how I verify it. So for each of these, I just run another tree evaluation. Good. Yeah, so open problems. Besides like what I already said, you know, extend to RAMs. That's probably the biggest one I think right now. Another one, extend to like alternating time. So alternating Turing machines with existence for all. This would be slightly stronger than showing it's in smaller space, like showing like you can do time t and alternating time square root tlogt or something like that. But even just getting so time t in space t to the 1/2 plus epsilon. For various reasons, this would actually give us if we could do this, we could do both of these. Yeah.
And this third one is even for a single tape pretty much.
Even for a single tape. Yeah, even for a single tape, getting something better. Yeah.
So I think I saw some follow-up, can you comment on those?
Which follow-up? Because which follow-up were you referring?
I don't remember the author, but. Maybe.
Well, one follow-up shows that circuit evaluation can be, the space bound for circuit evaluation can be improved to square root of s log s. In my paper, I just said square root s times pi log s because I didn't, because there's some overhead.
I see. So
That is a legitimate paper. Let me not comment on, I'm being recorded. Let me not comment on the other papers. So don't really believe everything you read in there.
So the circuit evaluation problem, like after using this, we'll still have some overhead.
Yeah, so when you apply like the multitape Turing machine for circuit evaluation, then apply this algorithm. So like the best algorithm I know for circuit evaluation is like s, maybe log squared s time on multitape, and so there'll be some extra log factors when I do the space simulation. But But yeah, a PhD student at University of Chicago showed how to sort of directly manipulate the circuit and sort of shave some log factors. Yeah.
So what about more application on the Mertz tree evaluation algorithm? It should be powerful, right?
It is powerful.
Yeah, and do you think like more applications?
Oh, does it have more applications? Probably there are more ways to apply it to things. It's certainly very, very powerful. I feel like, so, I mean, just to go back to one more time to this on time versus space 2 and 3 papers, right? So, right, they somehow were pebbling a T-node DAG without storing the DAG. So that's sort of how they were able to do it, like a computation graph in which you're computing just a bit in each step of each node. Here, right, we have some tree that we're forced to use because we're literally, solving the tree evaluation problem. We reduced to that. So maybe there is a way to think about what's going on in Cook and Mertz in a general way, which is not explicitly thinking about trees, but just simulating time-bounded computations. So it's maybe implicitly solving a tree evaluation instance. And if it's implicitly doing, we don't have to store this DAG. And if we don't have to store this DAG, then we can probably do graphs. Right? We can probably do something like that. If we don't have to store this like omega t sized graph, then there's no impediment anymore to simulating ramps. Yeah. So yeah, I think like trying to understand like how to generalize Cook Mertz so that like it's not necessarily like, looking at a tree, but like just simulating time, but like how they do it as opposed to how you would pebble. Yeah.
Wonderful.
Thanks.
Okay, thank
Thanks.
you.
Thanks.